Well, hello, everybody. I'm Dave Scott, and I'll be the moderator for this session that features Dr. Clain Jones from Montana State University. Clain is a soil fertility specialist. He's been so at MSU since 2004. He enjoys conducting research and sharing outreach on topics including cropping systems, soil acidification, nitrate leaching, and biological nitrogen fixation of post crops. I might add too that I've known Clain for a number of years now, and he's a top-rate guy. And so please, I wanted to remind you that that put all your questions in the chat box, in the Zoom chat box, please. We'll be trying to get to them as we go. We have a couple different places we're going to stop and take questions, and then also have questions at the end. So without further ado, may I please introduce Dr. Clain Jones.
Great, thank you so much, Dave. Good afternoon for those of you in the Mountain Time Zone and those of you further east, and good morning to those of you in the Pacific Time Zone. The picture that I have here on the front is of a Montana dust storm. One of the morning presenters showed a sad picture of a farmer and his two boys running to their house. I just wanted people to remember that those days are not completely over. We still have dust storms in the Great Plains and probably throughout the United States. I want to recognize my co-PIs on this study, Perry Miller, Kathy Svinsky, Stephanie Ewing, and Rick Engel. And if you don't get your questions answered today, please feel free to always send me an email or give me a phone call, and I'll do my best to answer those questions. So my objectives today are to show how crop rotations, cover crops, nitrogen fertilizer, and tillage affect soil chemical parameters, physical parameters, and biological parameters. And first, I want to get a little better flavor for who you are, and that might affect how I continue from here. So Marianne is going to show a Zoom poll. This is the first time we've tried it in this conference. Please put down whether you're a producer, crop advisor, agency personnel, extension or educator, a nonprofit, or a researcher. And again, that'll give me a flavor and also give you a flavor for who's attending this conference. Top 5 answers on the board. It looks like agency personnel and producers are head-to-head, very similar, maybe a few more producers, and then the rest of the categories are quite evenly split. So thank you very much for that. I'm going to end the polling, but we'll save this for our information for later. All right, so what are some agronomic tools that you can use to take care of your soil? Certainly some of those would be things like leaving more crop residue, not tilling for the most part, increasing your cropping intensity, meaning leaving fewer places available for fallow times of the year when things aren't growing. Think about your rotation and diversity and your nutrients and amendments. And then just kind of a thought question, I'd like you to think about what other things might affect soil health. Some examples of measurable impacts would be soil organic matter, soil nitrogen, and what's called PMN, or potentially mineralizable nitrogen, microbes and the enzymes that they release to make nutrients more available, aggregation, or those clumps of soil that help roots grow and help air and water make their way through the soil. And then also soil pH. Low pH is starting to become a problem in Montana, as I'll talk about later. So the basis for soil health is biological activity, and organic matter is really the fuel for that activity. To put things in perspective, 10,000 pounds of life exist in an acre of soil. So that would be from macroinvertebrates, worms, all the way down to single-celled organisms. That's the weight of an elephant. It's a lot of weight, especially when you consider how small those individuals are. When microbes die, part of that is recycled and is readily available to plants. The rest can end up associated or tied to mineral surfaces, which protects them from further decomposition. And this long-lived soil organic matter pool is especially important for improving soil structure, helping with water holding capacity, and increasing the ability of the soil to hold ions and other nutrients. Finally, all of these together determine soil fertility, which is my specialty. There's a lot of challenges of studying soil organic matter. One is that there's a lot of natural variability out there in the soil. In one study just to our north in Western Canada, they measured soil organic matter in a small plot, 2 meters by 5 meters, 2 by 5 yards. It varied in soil organic matter from 1.9% to 2.6%. So you can picture when you think you're going back to the same spot every year, every 5 years, you might not be. Soil organic matter increase is also slow. In that same study, they only found that the soil organic matter increased by about 0.1% over 22 years in semi-arid fields, across rotations, and across tillage. From that same study, what I'm plotting here on the horizontal axis is the 1996, the pre-study soil organic matter in the top foot. And then on the vertical axis, I'm plotting the change in percent soil organic matter in 22 years. So above the line means soil organic matter went up, below the line means it went down. So a few more soils went up than went down. The other very interesting thing to me is the higher the initial soil organic matter, the better chance that soil organic matter went down. The lower the soil organic matter, the better chance it went up. In some ways, that's probably a good thing because these soils maybe don't need that much soil organic matter, and these certainly do. There's a great, yep, what I just said there. So soil organic matter doesn't change much, but one really nice thing about soil organic matter is that small changes can make big changes in soil health. This is a study out of Australia where they looked at the effects of soil organic matter here on the horizontal axis in percent in the top 4 inches on water stable aggregates. So chunks of soil that don't get broken up or basically dissolve if they get hit by raindrops. So those are the types of aggregates that you want in your soil. Notice that relatively small changes, increases in soil organic matter, going say from 1.6% maybe to 2%, can double the amount of water stable aggregates, which will double a lot of things, things like infiltration rate, possibly root growth, the ability for water and air and other gases to move below the surface. A lot of Montana soils have soil organic matter in this range, somewhere in the low 2s. So we're in an area where it is fairly easy to increase water stable aggregates with relatively small changes in soil organic matter. So thinking about rotations, rotations are a tool a farmer has to increase soil organic matter. This is work again done to our neighbors to the north in Saskatchewan over a very long study from about 1960 to about 2010. And they measured the soil organic matter in the top 6 inches in tons per acre for 3 different systems. Fallow wheat, which was essentially their standard system back in the 60s, fallow wheat, and then continuous wheat. Not super diverse systems, but really showing the benefits of having more crops in the system. So notice how much higher the soil organic matter is in continuous wheat than either of the systems that had fallow in them. Today in Montana, I'm going to be focusing on 2 different studies. One is a mixed cover crop study conducted at 2 sites, Amsterdam and Conrad, both fairly dry sites. And here we looked at a 2-year rotation where the first year we had fallow or cover crop, the second year we had wheat. I'm also going to be showing some results from what we called a greenhouse gas rotation study that started in 2002. So now we're 18 years into that study. I have some data from 14 years in, some from 18 years in. Here, this was a more diverse system with not just cover crops and say wheat or fallow, but we had pea grown in a number of different ways, as a grain, as a hay, as a cover crop, a conservation reserve program system where we had alfalfa grass growing and then converted to a pea grown for grain. So I'm going to start with that second study first. Here what I'm showing is soil organic matter in tons per acre on the vertical axis, and then plotted on the horizontal axis is our 7 different rotations in that study. So tilled fallow over here on the left, no-till fallow, continuous wheat, pea grown for grain, pea grown for hay, pea grown as a cover crop, and then the CRP system converted over to grain. The red dashed line shows soil organic matter at the beginning of the study. So one thing to notice is that it didn't change very much, but the systems that decreased the most were tilled fallow. Kind of makes sense. You break up aggregates, you're not returning a lot of residue to the soil. The systems that did the best increase soil organic matter the most were continuous wheat and this perennial system. So what was really affecting soil organic matter in that study? When we plotted shoot residue input in tons per acre per year on the horizontal axis and soil organic matter change in tons per acre per year on the vertical axis, we found a very positive and direct line and what's called a very good R squared. So it might make sense to you, but we don't see this in every study. The more residue you leave behind, the better chance that you'll increase organic matter. Kind of an outlier over here is the CRP perennial forage system. Notice we didn't have to leave very much shoots behind to grow soil organic matter because a lot more of those perennial biomass is below ground in the roots. And what percent of residue carbon stays in the soil? In this study, it turned about 40% of the carbon that was grown stayed in the soil. We also see similar results in that mixed cover crop study. Here again, I plot the above ground residue in tons per acre against soil organic carbon in the top 4 inches at Conrad, which was a much drier site. And we see a weak correlation, but we do see a correlation. At Amsterdam, the slightly wetter site, we see a really strong correlation between the biomass returned and the soil organic carbon in percent. N rate, surprisingly, in this study did not affect soil organic matter. It didn't increase it or decrease it. My take-home message would be to select cover crops that produce high biomass over the rotation, so both cover crop and cash crop, if your goal is to build soil organic matter. Are there questions so far? I certainly saw some flying by in the chat, but I'm going to let Dave see if he wants to ask specific questions that he saw roll by.
Actually, Clain, we have some comments, but no questions so far.
Okay. I am going to keep rolling, but feel free to type those in, and Dave will ask me at the next question break that I have. So a little bit on diversification. How could you diversify your system, and how might it help soil organic matter at all? So one thing to think about is which of these practices do you use perhaps to diversify? Rotating species across time, so having a diverse crop rotation, mixing species within a field, so maybe having more than one crop grown at the same time, and maybe even mixing varieties within a field. I feel that diversification can really help with reducing risk. In our cover crop study, if, for example, our peas died, but we had lentils growing, we at least had something there that would grow. So I pointed out in that previous portion that the amount of biomass returned is really essential at growing soil organic matter. So in this mixed cover crop study, what I've done here is I've plotted the amount of total shoot biomass return, cover crop plus the wheat, for my 11 different treatments. Here I have tons per acre residue return on the vertical axis for fallow, which of course had the lowest amount, for 2 species mixes, for 6 species mixes, sol P, and then also my 8 species mix. And asterisk means that we had a different amount of biomass from this really diverse 8 species mix. So notice that some of these over here did not produce as much biomass. For the most part, a lot of these did produce the same amount of biomass as the 8 species mix. It looks like overall the number of species in the mix might not matter as much as you would think. So what does matter, or what did matter in this particular study? Well, the one group of plants that really increased shoot biomass was nitrogen fixers. That hopefully makes sense. We don't have a lot of nitrogen in our systems here in Montana. So here again, I plot the total 7-year above ground residue in tons per acre for both our sites, Amsterdam and Conrad, when I applied no nitrogen, a mid-level of nitrogen, and a high amount of nitrogen. The orange was our 2 species nitrogen fixer functional groups. The gray were functional groups or groups of plants that had no N fixers. Notice that in most of these cases, the N fixers grew substantially more biomass than the non-N fixers, about a ton per acre more residue in biomass, and therefore likely more organic matter. So how should you pick cover crop species? Well, first you need to identify what your goal is. Is it to produce more residue, produce more nitrogen, grow more roots or more forage? You have to balance the seed cost and the impact on the cash crop. Here in our semi-arid environment, if we grow too much biomass, we use up a lot of water and therefore hurt the cash crop yield the next year. Certainly want reliable establishment and growth based on biomass, reliability, and the amount of soil water that we left behind in our systems. I would say growing pea or barley, a legume taproot mix, and safflower in general all performed pretty well. And mixes did not use water or end differently than single species, at least in this study by Kahn and McVeigh, who are located in Billings, Montana. Mixes also often have less risk of total poor or failed production is one reason I like mixes. Rotations, of course, can also change plant available nitrogen and either lead to more or less leaching. Here over on the right, I show what is needed for leaching, which is high amounts of nitrate and high amounts of deep percolation. You need both to get high amounts of leaching. We definitely have both in fallow. We definitely don't have both when we recrop or grow a crop every year. So how can we keep more nitrogen in the soil, less fallow, more cover crops, more deep-rooted crops, planting fall crops, and supplying nitrogen with legumes rather than always with fertilizer? In this study located in Bozeman, we found that potentially mineralizable nitrogen, or the amount of nitrogen that is released by microbes each year, was significantly less for both fallow and continuous wheat systems than it was for a pea green manure. So PGM stands for pea green manure, with pea grown for grain essentially intermediate between the two. Keep in mind that nitrogen from legume cover crops will release nitrogen more quickly than legume grown as a grain. That has to do with carbon to nitrogen ratios. The end benefit will depend on the species, how long they're grown, how often they're grown, and also environmental conditions. Work out of Oregon has measured the plant available nitrogen from different cover crops. and found that legumes, especially when they're terminated fairly late, somewhere around bud stage, release a lot of plant available nitrogen. A system that had 75% legume released a fair amount. If you only have 25% legume, though, there was almost no plant available nitrogen release. And a cereal cover crop actually, especially terminated late in the season, actually used up plant available nitrogen. So on to soil acidity or low pH. Soil acidification is a major problem in parts of Montana. We just discovered this about 6 years ago. This is what a field looks like that has low pH, and it's highly variable because there's pockets of low pH and pockets of high pH. Low pH can change herbicide action. It can reduce nodulation in legumes, can increase disease of various crops, resulting in yield loss, soil organic matter loss because no residue is getting returned, and a loss of resiliency. So this is what an acidic field can look like. This is durum that is grown in a low pH field somewhere in the forest. Nitrogen applied at reasonable rates, meaning rates that are pretty good for yield and pretty good for protein, have been found to reduce soil pH in Montana. So again, this is based on that long-term rotation study west of Bozeman, where on the x-axis, I'm plotting the cumulative nitrogen input in pounds per acre over the 16-year study, and on the y-axis, soil pH in the top 4 inches. What we found was a pretty linear relationship. The higher the nitrogen, the lower the pH. Or an organic system didn't reduce the pH at all because nitrogen fertilizer is the cause of this acidification and is not applied in organic systems. The slope of that line is 100 pounds of N dropped the pH by about 0.04 units. Maybe not that all alarming. But in a sandier location in Montana, the slope of that line was a lot more dramatic, where 100 pounds of nitrogen dropped the pH by 0.14 units. Below 5 or so is where we see extreme toxicity. So this field is heading to extreme toxicity pretty soon. And then a pasture system that was heavily grazed and applied with a low amount of nitrogen, only 40 pounds of N per acre, had an intermediate pH drop, somewhere around 0.07 pH units per 100 pounds of N per acre. So which systems drop pH the most and which the least in that study? Well, there was really one loser, this wheat on wheat system, especially when it was applied at a high amount of nitrogen, dropped the pH the most. The rest did not drop pH very much. And excuse me, that was for the lower N rate system. These new bars here are for the higher rate system. So again, this wheat on wheat system dropped the pH down into the 5s. At our sandier site in Big Sandy, Montana, where John Tester is from, we found that soil pH was the lowest in our fallow and continuous wheat systems and highest in our legume that was grown for grain, likely a nitrogen rate effect. Some people attribute no-till as the cause of soil acidification, but the study in Idaho showed that it was really not. It's more due to nitrogen fertilization. So at the beginning of this study, the pH in the top few inches was somewhere around 6 to 6.4 to 6.8 soil depth over here on the y-axis. And then at the end of the study, the soil pH was down here in the 5s for no-till, minimum till, and conventional till systems. So not very big differences. No-till often does concentrate low pH in that top layer though, which happened here. One problem with tillage is it spreads that low pH zone across a deeper area, and then when you need to fix it, say with lime, it takes more tillage, and more lawn. So what can you do to reverse this? One would be to grow a perennial forage crop. In a study in North Dakota from 2006 to 2011, tracking soil pH in the top 2 inches, continuous spring wheat ended up reducing the pH slowly, whereas the perennial forage grown, which was a mix of alfalfa and grass or just straight grasses, actually resulted in higher pH than the continuous wheat system after several years. This little bit of information over here on the side of the graph was the years that it took to improve soil health for different parameters when you grew a perennial versus wheat. Somewhere between 2 and 4 years and soil health was improved. Any questions so far?
Oh, yes, Clain, we've got a number of them.
Okay.
I'll try to get through them as best we can here. If at some time you could comment on how or if you can calculate water holding capacities to soil organic matter, if you could briefly describe that, Clain.
How you would relate the two?
Yes, how they correlate.
Yeah, so as you increase soil organic matter, almost as a rule, water holding capacity goes up. I don't have a graph here, but there are some great graphs out there. Because soil organic matter is a relatively small part of the soil, most of the water holding capacity is controlled by the soil texture and substantially less by soil organic matter. But whoever asked that question can ask me for the graph I'm speaking of. Next question.
Next one is, Ann asked, what was in the 8 species cover crop mix that you had on the board there?
Right, so it's 2 N fixers, 2 brassicaceae, 2 tap-rooted, which included crops like safflower and turnip, and then 2 fibrous rooted species, essentially grasses, so canary seed and oats. So it was 4 groups of 2 species each.
So you were trying to cover all the bases there. Is that right, Clain?
Yeah, the big bases, yes.
Yeah. Ben asks, what is the method of quote unquote biomass return to the soil termination? Is the stubble tilled back into the soil or left on the surface?
Yeah, sorry. These were, for the most part, all no-till studies, so they were left on the surface.
Okay. Ann asks, did you notice a difference in response based on soil health of the field you were planting into?
Ask that one more time, Dave.
Did you notice a difference in response based on the soil health of the field you were planting into?
Oh, okay, yeah, like kind of the original soil health.
Right.
The soils were actually in a lot of ways pretty similar. Soil organic matter was right around 2 to 2.4%. There weren't as dramatic as you might think among the 3. So we did not really. It was more dependent, I think, on moisture. We saw bigger soil health increases at the wetter sites because they could grow more residue, was my thinking.
Okay, great. This is a question that often comes up. Steve asked, does it matter if you were adding green, still living cover crops via mowing or some other means versus brown senescent cover crops?
It should matter some. So the green will have what's called a lower carbon to nitrogen ratio, maybe somewhere around 15 to 25 to 1. That's a range that nitrogen will get released quickly. The residue will get decomposed quickly. Once it's brown, it's probably more in that 25 to 60 or 80 range. It's going to break down more slowly, which sounds bad, but that actually can be good because if it breaks down slower, more of it gets converted to soil organic matter and less of it gets converted to carbon dioxide, which can go up to the atmosphere.
Great. Jeff asks, how much crop diversity can promote soil health, not just cover crops, but peas, lentils, wheat, oilseeds, green manure, safflower, etc.? In short, don't we need great diversity, livestock integrations, and more complex rotations to promote soil health?
It depends what Jeff means by need. Certainly, we saw improvements in soil health and what I would call, relatively simple system, 2-year rotations, no livestock. But yeah, I agree that the more complex and diverse the system, generally the more resilient it's going to be, and possibly the more improvements in soil health. But it's hard to find those studies that actually demonstrate that for sure. Good question.
Thank you, Clain. Kind of following up on that, this is a little bit political, but do you think that the timing of cover crop termination ought to be left to the farmer and not to the guidelines of the risk management agency?
Yeah, that is somewhat political. So what we advocate pretty strongly, by we, Perry Miller, my colleague, and I, is terminating somewhere around early pea flower, because we find from flower to pod, the cover crop uses up so much water that we really hammer the next year's yield, and we actually really hammer the amount of stubble left behind. So somewhere on flower is pretty good. And yes, if that does get challenging if your insurance or somebody else is telling you you need to terminate that at a different time.
Well handled, Clain. The next question is, are these soils that you were talking about in the 2 test studies naturally alkaline? Where did they start to begin with? I guess
Right.
that's what he's
So,
asking.
The 2 of the soils were pHs very close to 8. At Amsterdam and Bozeman, they were almost 8. At Conrad, they range from about 6 to 7. So
Okay.
more neutral.
And then Susan asks, is the N fertilizer application a one-time application or was it over many years?
Yeah, many years. So we were feeding the crops, applying nitrogen, similarly how a producer would apply it somewhere. We apply 3 pounds of available nitrogen. That means soil test nitrogen plus fertilizer per bushel of wheat grown to get good yield and good protein. So it was applied every time there was a wheat crop, and it was never applied in a cover crop.
Okay, just a few more, Clain. Byron asks, in dry climates, have you seen a benefit if the cover crops were rolled down on contour rather than perfectly straight rows? I have seen several videos in Montana where they roll the cover crops and plant in a single pass.
Yeah, we did not roll these. We have experimented with like crimp rollers and other studies, but these were just sprayed out with herbicide.
Okay. Last question. How many years were the perennials left in the rotation?
10. So it was 10 years and then 4 years of annual cropping after that before we took our pH measurement and soil organic matter.
Right. I guess we have one more, Clain, and this one you kind of alluded to already, but is soil acidification an increasing problem in dryland systems, and how do we prevent this problem?
It's really quickly increasing. So again, in 2015, we hardly know it existed. We estimate there's 500,000 acres in Montana. We know there's other acreage in the Dakotas, Idaho, Washington, and Oregon, almost all in dryland. We prevent it by really watching our nitrogen, by affecting our crop rotation to have more legumes and more perennials. If we grow wheat on wheat on wheat, high N rates, that's going to be a problem. Organic systems don't seem to acidify because they are not applying nitrogen. So there's many ways, and I have a lot more information than just that I can share.
Okay, well, let's go on further. Thank you, Clain.
All right, thank you. Great questions, everybody. So speaking of tillage, this is a graph that shows the effect of spring tilling in the spring one time versus no till on soil organic matter. And the graph is from the surface on down for the top 12 inches, 12 to 24 inches, and 24 to 36 inches. Different letters mean that the differences are significant. So no-till produced higher soil organic matter in the top 12, the 12 to 24, and in the 24 to 36 inch zone compared to one-time tillage in the spring. In a study done in Wyoming by my colleague Jay Norton, as well as some other scientists, looking at soil organic matter in tons per acre for grazed native range, basically as a control where there was a lot of soil organic matter, wheat fallow that was highly tilled had relatively low amounts of organic matter, as did a continuous mixed crop that was minimally tilled, as did a continuous mixed crop that was no tilled. So here, there were not large differences in soil organic matter. The only one that did fairly well was CRP. So again, Conservation Reserve Program, a perennial crop that puts its roots deep, puts a lot of energy and biomass below ground, had relatively high soil organic matter. One thing that's come up with partly with this acidification issue is one way to fix soil acidity is to lime the soil. But a lot of farmers are rightfully concerned that by tilling, they might undo all of their gains they've made with no-till. So we really got into the literature. Does occasional tillage, meaning one-time tillage, say every 10 years, undo the gains from no-till? Well, of course, it depends. It depends on the tillage method, how aggressive it is, the depth, the timing, the soil temp, and also the water content at the time of tillage. But overall, these studies have found that one-time tillage does not reduce soil organic carbon. We found that in Montana. Does not reduce soil water or aggregation, but it does reduce the vertical stratification of soil organic carbon and nutrients, which is actually could be a good thing. The impacts of occasional tillage when they were negative on soils and crops generally were short-lived. Some benefits of occasional tillage were weed control, incorporation of lime or nutrients, and a reduction, sometimes a short-term reduction, but a reduction in compaction and also in large pore leaching, which can happen in long-term no-till. Some strategies to reduce the need for occasional tillage, or maybe the detriments of occasional tillage, would be what's called controlled traffic, driving in the same place in a field, using cover crops, diverse rotations, and possibly amendments. This is the study I alluded to in Montana, where my colleague Rick Engel measured soil organic carbon before tillage was performed by the farmer, and then after tillage was performed the next year. And what he found was actually almost a perfect one-to-one line, which meant that soil organic carbon didn't crash like some of us might have hypothesized. Infiltration rates were mentioned in an earlier talk by Allison, I believe, this morning. We measured infiltration in that long-term study west of Bozeman for our 7 different treatments, and we found what I thought was really amazing, which was that infiltration rates measured in inches per minute were 7-fold higher after all of these recrop systems than our 2 fallow systems. So just growing a crop every year really dramatically increased infiltration rates, probably because there was more root exudates, more aggregates, a better ability for water to pass through and between those aggregates. Something else that can be affected by crop rotation and cover crop is soil temperature. This is work that we did several years ago where we grew fallow, sol pea, and an 8-species mix, and then we measured temperature at 2 inches down in Fahrenheit. Notice the fallow system in yellow was sometimes 10 to maybe 15 degrees warmer than our 2 cover crop systems, but our 2 cover crop systems didn't vary at all. 1 species or 8 basically just shaded the soil. Question might be, well, what's the benefit of that? Certainly one benefit would be less evaporation. There's probably other benefits to microbes by having cooler temperatures. Covers have also been found to increase microbial biomass in Montana. Again, looking at that mixed cover crop study at our 12-inch site and our 14-inch precipitation site for summer fallow, the full species mix, and P on microbial biomass. What we found was that the two cover crop systems had significantly higher microbial biomass than summer fallow, and the P at our second site had substantially higher microbial biomass than in our summer fallow system. In similar work conducted by our Canadian neighbors, looking at the number of organisms per gram of dry soil for both fungi and bacteria, the fallow system and the wheat system had far less microbes than our 4 legume systems, all grown in rotation with wheat. So how can you manage for healthy soils? Well, based on our studies, feeding soil microbes with residue is really a crux of healthy soils. Keep in mind, it takes time to increase soil organic matter. Maybe the only exception would be if you had high quantities of compost or manure, then you can build it quickly. With crops, it takes a lot longer. We found that increased residue with increased crop frequency or with cover crops built healthy soils. Cover crop biomass and including legumes appeared to be more important than the number of species in cover crop mixes. And in general, legumes seem to need to comprise more than about 40% of a cover crop mix to contribute soil available nitrogen. And by that, the final amount of biomass needs to be more than 40% legume. And finally, legumes to reduce nitrogen fertilizer will also help minimize soil acidity. Other things you can do, perennials can reverse acidification. Perennial and no-till systems greatly improve soil organic matter, though slowly. Recrop definitely increases water infiltration. No-till covers can moderate soil temperatures, and soil microbes benefit from moderated temperatures and having legumes in the cover crop. If you want additional information, you can go to my webpage where there's sites on cropping systems, sustainability, soil health, soil acidification, and you can hopefully find more questions answered there. Any questions?
Okay, great. Thank you for your presentation, Clain. We'll move on to some questions. First, Susan says, nice infiltration study. She liked that. Kent asks, how was infiltration measured in the Montana study you measured? I imagine specifics.
Right, so we used a double ring infiltrometer test. And so it just means a ring inside of a ring. And then we poured water into both rings and we measured how fast water fell in that inner ring. So it's what's called a saturated infiltration test. The downside of a saturated infiltration test is rarely in Montana are our soils saturated. So other people use sprinklers. They're a lot more involved and harder to measure. But yeah, we use double ring infiltrometer test.
So I've got a question for you on that, Clain. What is the advantage of a double ring versus a single ring?
Yeah, so with a single ring, water can move out laterally. And so what you're actually measuring is not just how fast water moves down, but how fast it moves laterally. By having a separate ring of water, that inner ring water only has one place to go. It can only go down. It can't really move to the sides because it's already wet there. So it's it's somewhat more accurate than a single ring infiltrometer test.
I see. And you're putting down the same amount of water, right? Same inch of water.
You keep the same amount of water in both rings, but you only measure the drop of water in the inner ring.
Right. Okay. I did want to mention right now that for those of you that are signing up for continuing education credits on the screen now, you can see the QR code and use that sign up sheet also. Then we have another question. Clain, what is the effect of terminating cover crops with herbicides? How does that affect the soil microbiome, soil organic matter, etc.?
Yeah, I don't have as good a handle on that as I should. There's a number of studies out there. I would say the most of them are on with glyphosate, and there's some papers that show effects and others that um, don't show effects. Compared to, say, haying or grazing or plowing, what we see is often a slower death of the plant, which means more water use, which often can be bad for the next crop.
Okay. Clain, when you talk of occasional tillage to incorporate lime, what time frame are you thinking of? Every 10 to 15 years with a chisel plow?
So yeah, people have used duck foot plows, they've used chisel plows, they've used tillage. I'm sorry, they've used hole openers. There's been a lot of ways to get lime down into the ground. But as far as a time frame, what we are thinking is that you might only have to apply a large rate, say 2 tons per acre every 15 to 20 years. And that's based both on calculations of how fast does the soil acidify, and a study done in Canada that showed that pH stayed elevated after lime for about 24 years. But yeah,
Wow.
one time every maybe 15 to 20 years. The other hope is that people with Lyme recognize they don't want their soil acidifying and use more prevention practices so they don't have to lime in 15 years.
And Clain, are you speaking, when you're saying lime, what is your source of that lime? Are you speaking of beet pulp lime or a pelleted lime pellet?
So yeah, so any of the limes will work. In Montana, people are gravitating to spent lime, which is a waste product because it's free at the source. But pound per pound of calcium carbonate or lime, they behave pretty similarly. The spent lime is just the least expensive of the limes that I've seen.
Are there some problems with application with the spent lime?
Yeah, the spent lime's a little chunkier than, say, ag lime or pelletized lime. An advantage of pelletized lime is you could put it through a direct seeder and not have to till, but you can't put very high levels at that rate, and it tends to cost a lot more than ag lime or spent lime.
Right. Okay. Ben asks, do you have any suggestions for fall seeded crops to follow harvested cash crops for winter cover? Any winter hardy covers that will survive along the Canadian border, top of Montana?
Yeah, so it matters a little bit which side of Montana. So if we're talking Culbertson or Scobie in the northeast corner, there's almost no winter hardy cover except for winter wheat, which doesn't make it every year up there, as Ben probably knows. If we're talking north of Kalispell, where it's a little more banana beltish, then winter peas, winter lentils would be two choices that I would gravitate to.
Okay. Darman asks, where can I find the information for the correct parameters to look for when I do my occasional tillage so I don't undo my no-till practices, i.e. the depth, soil temperature, water content?
Yeah, good questions. I think in general, I think about the immediate effect of erosion. And so, for example, if it's dry and windy, not a great time to till. If it's really wet, then you end up clotting up your soil, and that's not necessarily good. I would say that Darren should probably email me because there's a lot of considerations there.
Okay. Clain Jeff asks, some have suggested that biochar will hold moisture and reduce acidification as well, or better than lime. Any comments on that? Have you had any experience?
I haven't had experience. one issue certainly is to correct acidification, we're looking at tons of products. So we need tons of lime. Biochar is possibly not as strong as lime at reducing acidity. So we're going to need tons of the product. And I've seen costs of biochar pretty expensive. But yeah, if you could get it for free or low cost, it tends to be fairly high in pH. It has a fair amount of buffering capacity. So it's going to really come down to cost. But lime pound per pound is probably going to be somewhat better than biochar.
Okay. One more question we have. There is some research that across the soil profile, including sampling that is fairly deep, that organic production systems have the highest level of soil organic matter. Why don't we promote organic systems to promote soil health?
Yeah, so, a grad student of mine did some research on organic versus no-till, and we actually found no differences in soil organic matter. That might be different in different regions, especially in the Midwest, where there's a lot of manure available and a lot of manure applied on organic systems. So unfortunately in Montana, there's trade-offs. So, no-till has negatives, including, say, herbicide use. Organic has the problem of we really haven't figured a good way to control weeds without tillage. And so tillage ends up decreasing soil organic matter. Organic tends to be more diverse rotations than no-till. So there are all these trade-offs that end up resulting in maybe somewhat similar soil organic matter. But there's certainly, advantages to both systems. And if we could get organic more minimum till or even no-till, I think it's going to be a huge winner for soil health.
Clain, I have a question about that. What is your take on integrating livestock into these organic systems in an effort to reduce the tillage for weeds and things?
No, I think it's a great idea, both in the organic systems and in some of the no-till systems. We have challenges in a lot of our areas with water, and some of those no-till systems where you're up on a plateau or a bench away from water. But yeah, I see good advantages, and other people here in MSU have studied those more integrated systems more than I have. Pat Hatfield will talk later about some of his work.
Oh, great, Clain. I do want to put a plug in for a grazing exchange that has just been put online. It's called Intermountain West Grazing Exchange. It's free, and if you've got cattle or sheep that you're looking for a home to graze cover crops or crop residual, then you can surely post on that site. And if you're a crop farmer that is looking to get livestock into your system without investing in the livestock or the time it takes to calve them out or lamb them out or whatever, this is an excellent opportunity to just go to Intermountain West Grazing Exchange and put your ad on it. Let's see if we have, there's one comment maybe you could speak to. Wood ash is an excellent liming agent as long as the potassium isn't already too high. Have you any experience with wood ash, Clain?
I have not. Sodium can sometimes be a problem with wood ash or just salts in general. But if we had huge piles of it in Montana, it could really work. One issue is we're talking about tens of thousands to hundreds of thousands of acres, and so we would just need a lot of wood ash in order for it to be effective, and then a good way to apply it. And I have an impression of it as being kind of light and maybe has an ability to blow. So if it was pelletized, some way you could put it through a no-till drill, I think it could work great.
Okay, and we did have one reminder from Catherine Olson at Montana State University that if you're interested in getting Clain's PowerPoint slides, just contact her at Catherine Olson or .olson@montana.edu. It's in the chat box, and she will send them to you. So that's great. Thank you, Catherine. Let's see, I think we're about to the end now. We want to just say one thing, that this presentation by Dr. Jones was recorded, and it will be available through Whova in a few days towards the end of the week. And if you did not get, if you think of a question that you did not get a chance to express today, just type it into the Whova question and answer pane after this Zoom session is over, and we will try to get back to you. So with that, I want to thank Clain very much for his excellent presentation, and I sure hope that it has helped some of you, and I think it really has, because but judging from your questions, it's really been a great discussion. So thank you very much, everybody.
Yep. Thanks for the questions, everyone, and thanks to you, Dave, for moderating. Great job.
You bet. Thank you. Thank you, Clain.